So closure. Okay. So you have, call the notation. You have X be a metric space. You've got some subset of X. We defined E prime to be the collection of limit points, the set of limit points of your set. And then we defined this thing called the closure, right? Closure of E, which is denoted E with a bar over it. Okay, bar over it, and that's defined as what? What's the closure? E union E prime, right? So you take E and then you take E prime, and then you take E and its limit points, you put those guys together, and that's called the closure. Okay. So then we've got this theorem about properties of the closure, or properties of the closure. So first off, the closure is closed. The closure is a closed set. The set is closed if and only if it equals its closure, right? So if you take the closure and then the set doesn't change, that means that that the set was closed to begin with. C, if E is contained in F and F is closed, then the closure of E is contained in F.
Is it just because E is equal to the closure? That is why, since E is enclosed, so then the closure is also closed.
Not exactly. Something like that, but not exactly.
Okay.
Okay. So okay. So let's think about this first one. Why should E bar be closed? Why should E bar be closed? So think, right? You've got your set E, and you've thrown in all the limit points, right? And what we're saying is that that set is closed. What does it mean to be closed? What does it mean to be closed, Max?
The set contains all of its limit points.
The set contains all of its limit points. Okay, so that means that you're taking the set and you're throwing in all its limit points. You're making a new set of set plus limit points. Then you're looking at the limit points of that new set, right? Of the set with the limit points thrown in, and you're saying that those limit points still have to, or were already in the set, right? Those limit points were already in the set. Okay. Okay. So okay. So does anybody have an idea of how to prove that, or why that makes sense? So, the best thing what you want to do when you encounter these sorts of things is to develop a sort of intuition about it, right? Like, why should this? Can anyone come up with a sort of a picture or like some sort of argument of how this ought to be true, right? So you've got your set already, You've got the limit points of that set, and now you're taking a limit point of the new thing, right? So you take E, you take E prime, right? And then you take, right? Then you're looking at the limit points of that, right? You're taking the limit points of that, and you want to say that that's actually the limit points are already in there. Right? The limit points are already in that set. Okay. 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 So Okay, so sorry, I have one proof down here already, and then I thought I would try to do a different way, but maybe I shouldn't try to ad lib. I shouldn't try to ad lib for the class. Okay, so yeah. Well, actually, maybe it's useful. Okay, so you guys can watch me mess up a little bit. Okay, so here's how I think to think. Okay, so say okay, let P be a limit point of E union E prime. Okay, right? We're hoping to show, we want to show that this P is actually in E union E prime to begin with. Okay. Okay. So okay. So this guy is a limit point of E union E prime. What does that mean? What does that mean? That means that so in other words, given any radius, the punctured neighborhood of P actually intersects E union E prime. Right? Right? The punctured neighborhood actually intersects E union E prime, and we're trying to show that that P is either in E or is a limit point of E, right? So we want to show that P is in E or P is a limit point of E. Okay, that's our goal. All right.
Never mind.
Okay. 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 So suppose that P is not in E. Suppose P is not in E. Okay. And let's show that P has to be a limit point of E. Okay. We'll show that P is a limit point, right? That P is a limit point of E. Okay, so what do we need to show that it's a limit point? We need to show that in every punctured neighborhood of P, there's somebody from E in there, right? From every limit point, right? We want to show, sorry to be so pedantic, but we want to show that given any radius epsilon, that the punctured epsilon neighborhood actually intersects E. Right? Okay. Okay. So so you've got this P and you've got this radius epsilon, right? You've got this P and you've got this radius epsilon, and you say, okay, well, P is a limit point of E union E prime, right? So since P is a limit point of E union E prime, right? We know that either there's somebody from E in there, or there's somebody from E prime in there, right? So either there's a point from E, or a point from E prime in that punctured neighborhood. Right? Okay. If it's in E, then we're done. Right? If it's in E, well then the intersection is non-zero, is non-empty. Right? If it's from E, then we're done. Okay. Suppose it's from E prime. If it's from E prime, okay, then let's call that point X. So there's some point X from E prime in there. Okay. We want to show that there's a point from E in there. Well, how do we do it?
Take a neighborhood of radius epsilon minus the sets of epsilon.
Exactly. Okay. So you say if it's from E prime, then it's a limit point itself, right? So let delta be, say, epsilon minus the distance of p to x, right? Let delta be epsilon minus the distance from p to x, right? Let delta be the distance to the boundary, right? Let delta be the distance to the boundary, right? And then we know, since it's a limit point, we know that the delta neighborhood, the punctured delta neighborhood of x contains some point of p, contains some point of e, contains some point of e. Right? So either way, you're going to end up with some point of e, right? Either there's a point of e there to begin with, or there's some limit point of e, but being a limit point of e means that in this punctured neighborhood, there's some element of e. So either way, there's some element of e, and so we're done. Okay. Okay. Everybody all right? Yes, all right.
Sorry, just to clarify, the line, the function neighborhood of P with radius epsilon there at the bottom on the left side,
Mhm.
that's intersecting E, right? Not
Yeah.
E prime.
Not e prime, yeah. Right? We wanted to show that P was an e prime. In other words, that every punctured neighborhood will intersect E. Okay, was that okay or was that not okay? So I heard, so there's a famous mathematician named Calderon, Alberto Calderon. And what I heard, I don't know if this is a good thing to say, but apparently Calderon would come in and would just solve things. That is, he would just come in and figure things out before the class to let people see how he was thinking. So I don't know if that's a good thing. Yeah, maybe you need to be as great as Calderon to do something like that successfully. But anyway, I thought it'd be nice to show you how things can be worked out. Just to amuse you, let me tell you one story about Calderon. So the mathematician Zygmunt was teaching in Argentina one time, and he was teaching this class out of his famous textbook, Trigonometric Functions, and he sees one student in the class who's like making faces, scowling, and he says, what's wrong? You seem to be unhappy about something. What's wrong? And the student says, Professor Zygmunt, that is not the way that you prove this theorem in the book. You prove it in a much more clever manner and in the textbook. And Zygmunt says, no, I actually prove it like this in the book. And he says, no, you proved it in a completely different way that went like this. And over the course of their discussion, Zygmunt realizes that Calderon has not read the book. Rather, what Calderon has done, he's read the statements and then read the first line of each proof, and then tried to prove the rest on his own. And so he's come up with his own proofs, and like some of them are very superior to the ones that Zygmunt had come up with. So he invites Calderon to come back to Chicago with him. And in 1 year, Calderon completes 3 revolutionary papers, puts them together as his thesis, and is out with his PhD. Anyway, so Helen.
So we wanted to show that P exists in E union E prime. So we wanted, or like the set of limit points of E.
Well, yes, that's right. Sorry.
Yeah. So we wanted to show P exists in E, or P is a limit point of E.
Yes.
So we suppose P is not an E.
Very good. Yes.
How do we show that? And then we showed if it's not an E, then it's a limit point.
Yes.
But does that show then that P is an E or P is a limit point?
It does, because what it says is that if it's not in here, then it must be a limit point, right? So if it's in there, you're done, right? So there are 2 possibilities, right? if P is in E, we're done.
Okay.
We're done from the beginning, right? Well, now suppose that P is not in E. Then P is forced to be a limit point.
Oh, I see. Okay, cool. Thank you.
No, yeah, I thought somebody would ask about that. Okay. Okay. Any other questions? Okay. So the proof in the book is different, but and this is just for your amusement. Okay. So yeah, everything, just for your own entertainment, you can try to prove everything in the book in a different way. If you don't like it. Okay, so let's go on. Sorry to. Okay, so E is closed if and only if E equals its closure. Okay, this is actually pretty straightforward, right? The reverse direction, if E equals its closure, we just show that the closure is closed. That's the end, right? Right? If E equals its closure, E bar is closed. End of proof. Right? So the reverse direction is clear, right? If E is closed, that means that the limit points are contained in E. Right? That's what closure means. Right? And if E is, that's what being closed means. If E is closed, then it contains its limit points, right? But then, it contains E bar, right? Because it contains E and it contains its limit points, right? So that tells you that E bar is contained in E, which is in turn contained in E bar, right? So that tells you that E and E bar are the same. Right? Okay, so these are simple ones. The last one, if E is contained in F and F is closed, then E bar is contained in F. Okay, so you say, well, look, E is contained in F, right? E is contained in F. So if X is in E prime, what does that mean? It is a limit point of E, right? It's a limit point of E, so every punctured neighborhood contains some element of E, right? But every element of E is an element of F, right? So every punctured neighborhood of X contains an element of F because it contains an element of E, which is contained in F, right? What does that tell you? That if you're a limit point of E, then you're a limit point of F, right? Limit points of E are limit points of F, right? Because every punctured neighborhood is going to contain some element of E, but E is contained in F, and so that's true. Okay. So E is contained in F implies that E prime is contained in F prime. Okay, E prime is contained in F prime, but then what do you see? Well, then E union E prime is contained in F union F prime, right? But that says that the closure of E is contained in the closure of F, right? But the closure of F is F, right? Because F is closed, right? So E bar is contained in F. Right? If F is closed and E contained in F, then E bar is contained in F. Mr. Dent.
Yeah, so E bar is the smallest closed set containing E.
It is. It's, so I think that's a homework problem. I'm not sure if it is a homework problem, but it should be a homework problem.
What you just shown.
Yes. That's true. Yeah. So if you take the intersection combined with the previous theorem, which I skipped, if you take the intersection of all closed sets containing E, then you'll get the closure. Then you'll get the closure. So I hope it's not a homework problem. Okay. 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 Next theorem. Actually, no. Let's. Sorry. Let me go on to next idea, which is relative openness. It seems like a lot of people were confused about. Oh yeah, Susan. No. Okay, relative openness. So notice. If you have a metric space, okay, and you have some subset of the metric space, right? Well then, just use that. It's still a metric space, right? If you use the metric from the ambient space, well, it's still going to be a metric, right? So your y with that metric is still going to be a metric space. Okay. However, the notion of neighborhood may change. Okay, and so let me give you an example of this. Okay, so suppose I'm in R2, right, and I'm with the standard Euclidean metric. Okay, so my x is R2, and my y is the x-axis. My y is the x-axis. Okay, so and I give it the metric that I get from R2. Okay. Okay. So what's an open set, right? What's an open set in YD? What's a neighborhood in YD? If I take a point here, what's a neighborhood? Well, the neighborhood is going to be this, right? It's going to be some interval of some radius, right? Okay. But that's not an open set in your original space, right? This neighborhood in Y is not open in X, right? It's not an open set in X, right? Because to be an open set in X, I need to contain neighborhoods in the X sense, right? I need to contain neighborhoods in the X sense, and nobody in here contains a full neighborhood, right? They're all, one-dimensional. Okay. So this is what we mean by you're open relative to Y. This guy is open relative to Y, but it's not open relative to X. Okay.
Sorry, and the reasoning is that because it doesn't contain any of the elements of X?
It doesn't contain an open, if I choose a point here, for this set to be open in X, it would have to be that every point is interior in the X sense, right? In other words, I have to be able to find a disk, right, that was contained in that set, but I don't have a disk that's contained in that line, right? There are no disks in that line. Okay. So yeah, that's the definition here, right? That E is open relative to Y, right? If for all P and E, there exists R greater than 0 such that the Y neighborhood is contained in E. Okay, so right, this thing is a neighborhood of P in Y, right? A neighborhood of P in Y, not a neighborhood of P in X. Okay. Okay. Or, for example, suppose I take suppose I take y to be the open interval 0, 1 here. So x is the whole plane. Y is just this open interval here. Y is the open interval here. Okay. Within the world of y, if I take the whole set here, then it contains all its limit points, right? It contains all its limit points, right? So this set is actually closed, right? Or actually, let me make it even funnier. Okay, so I'm going to take x to be r. This is in response to somebody's question. Right, I let x be r, and I let y be the interval 0, 1. Okay, this is a metric space, right? And is it closed? If I take the whole set, well, it's closed, right? Because it contains all its limit. Within the world of y, it contains all its limit points, right? It contains the whole space, right? So it contains all its limit points. All right.
Wouldn't 0 be a limit?
0 is not in y. Within the world of y, there is no 0. You only have things between 0 and 1.
So in the world of y, 0 doesn't exist.
Right, there is no 0, right? I don't have to worry about 0 because 0 is not in my space. 0 is not a limit point. 0 is a limit point of y within the x world, but not within y's own universe. Okay. So this would be an example of a set that is closed. It's actually both open and closed with respect to its own topology, but within the greater set, it's an open set. Okay. Okay. So let me just, for now, state a theorem that I'm going to use in this. So it's a characterization of open relative. Okay. So you have some E contained in Y, contained in X, and X is a metric space, X a metric space. Okay. And so the theorem says that, what does it mean to be open relative to Y? It means that E is the intersection of Y with some open set. In X. Okay, so being open relative to Y means that you take some set open in X and intersect it down to the smaller metric space. Okay, so in this. In this example here, right? So here we have X being the whole space and Y being the x-axis here. Okay. What it's saying is that anybody who is open, it's saying two things. One, that if you take an open set in X and you intersect it with Y, then you get something that's open relative to Y. Okay. And it's also saying the opposite, that anything open relative to Y is obtained in this way. Okay. Anything open relative to Y, if I have some set open relative to Y, then I can actually think of it as the intersection of some open set in X intersected with Y. Okay. So this is a characterization of these sets. Okay. Let's prove that actually. So I was gonna save that for later, but let's prove it. Is everybody following me? So we're talking about this notion open relative to y, right? And what we're saying is that open relative to y just means that you are the intersection of some set open with respect to x with y. I'll say it again. Okay. Open relative to y, right? There are these things, open relative to y, right? And it turns out that open relative to y has a simple meaning. It means that you are the intersection of some open set in x with y. Okay, so, right? I say like, okay, so let's prove it. Let's at least do part of that proof. The proof is pretty straightforward, so I think I'll probably just do half of it. Okay, so open relative. Let's do the first direction. Let's show that if E, suppose that E is open relative to y. Okay, suppose E is open relative to y, and we want to show that there's some sort of superset that E is. So that E is intersection of that set with y. Okay, right. E is some sort of slice of that set. Okay. Okay. They say, okay, well, E open relative to y. What does that mean? That means that E is no. That means that every point, right? For every point in E, for every point P in E, there exists some radius, right? There exists some radius, I'm going to call it R sub P, such that the neighborhood this neighborhood is contained in E. Okay, so here's the picture. Think of this guy as your E. Okay. Think of this guy as your E. And what we're saying, E is open with respect to y. That means that every point is interior. Right? Every point is interior, so if I take a point here, then there's some neighborhood of it that's contained in E. That's all I'm saying, right? If I take a point in E, there's some radius so that that neighborhood around it is contained in E. Okay. So now we want to make a G that this thing is the intersection of with y. Okay, so how are we going to do it? We're just going to bubble everything out, right? We just expand everything out to like you say, okay, I've got this thing. I'm just going to flesh it out. Okay, so yeah, this is sort of obvious, right? Let G then be the union of the sets Q and X now, such that the distance from P to Q is less than RP. Right, take the union over all P and E. Right? So you just bubble everything out, right? Whatever you did, you take all these bubbles, and the union of those bubbles is G. Okay? And then G is open in X. Right? Because it's a union of open sets. It's a union of neighborhoods, right? And of course, E is the intersection of Y with G. Okay. Okay. And then the proof of the reverse direction is almost the same thing. You just reverse it. Okay. So I'll let you read that. But is this okay? Right? 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 If you're open relative to y, that means that there's some interval. Right? In my picture, it's an interval. There's some neighborhood around here that lies inside your set. Well, just take the neighborhood in the x sense and take the union of all those x neighborhoods, and you get the set whose intersection with y is your original set. So anything open relative to y can be realized as the intersection of something open in x with y. Yes,
Could you
Maya?
define how you, could you explain how you define G again with
Yeah.
the union notation?
Yeah. So, right, for every, this is the point, this was the set E, right? This was the set E. And we know that for every point in E, there's some neighborhood of P that's contained in E, right? That's what it means to be open with respect to Y. Okay. So for every point, there's an interval like that, right? There's another P, there's an interval, there's another P, there's an interval, there's another P, there's an interval. Take all those intervals and expand them out to neighborhoods in X, and take the union of all those guys. That will give you an open set in X whose intersection with Y is E. Yeah, Susan.
Is the union going to be a big circle in this case?
In this picture, I mean, it could be, yeah, it could be. Yeah, it sort of depends on how you do it, right? Like, right, because I could cover every point with a tiny interval like this, right? In which case, I'm never going to get a huge. Right? It depends on how I choose my reading.
But it doesn't matter.
It doesn't matter, right? All we want is that there is some open G in X whose intersection with Y gives us E, right? And so we can make lots of them, right? You could go, right there, right? Right? All you care is that there's some G that will work. Oh yeah, bam.
Can you explain why E is necessarily the intersection of Y and G?
Well, remember what E is. E is going to be the union of these intervals, right?
G? Wait, no.
So E is all these points P, right? But each of these points P is contained in the interval in X, right? Each of these things, each of the P is contained in some interval like that. But that interval is contained in the set E, right? So if I take the union of all these intervals, then I'm going to get E back. Okay. Okay. So now G is the union of so now G is the union of all these disks, right? Of all these disks. But you see what happens if I take the intersection of this disk with Y, I'm going to get this interval back, right?
Okay.
If I take the intersection of this disk with Y, I get this interval. So, right? So I think that is that enough, or is that clear?
So the interval is not the function neighborhood, but instead.
No, it's a full neighborhood.
Okay.
Yeah, it's not a function neighborhood. Right? It contains P also. It contains P also. Okay. Edward.
Oh yes, the way I see it is, each is like an open disk. You just want a horizontal cut of the disk so that it's contained. Therefore, the intersection will gives you back the whole. So, so that makes it perfect. Yeah.
Okay, thanks. Okay. 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 Okay, so we have a few minutes. I should probably stop. Okay, so let's at least try to get the first idea, first glance at this important notion of compact sets. Okay. So this is one of the most important ideas, and it's kind of hard to get. Okay, so I think the best way of thinking about compact sets is that it is the notion of compactness is sort of like finiteness for infinite sets. Okay. Finiteness for infinite sets. Okay, so you've got an infinite set, but there's some sort of finite quality to this infinite set. Okay, and that's captured in this definition of compactness. Okay, so it's and when you're doing your proofs about compact things, one way to start off is to say, well, suppose my set is finite. How would I prove the statement? Okay, and then you say, okay, I don't have finiteness, but I do have compactness, and then that allows you to get to some sort of finiteness, which allows you to prove it. Okay, so that should be your strategy. Okay, but the definition of compactness is very bizarre. Okay, so it's not bizarre, but it's a little tricky for at first encounter. Okay, so you have X a metric space, you have E a subset, and we first define this thing called an open cover. So any collection of open sets G alpha, where alpha range over some set of indices, open sets in X, such that their union covers E is called an open cover. An open cover of E. Okay. So to just give one example, right? If I have E being the real line, and I cover every point in the real line with some radius 1/2 neighborhood. Okay. So you take every single point and you cover it with an interval of radius 1/2, an interval of length 1. Okay. So everybody is covered with an interval of length 1. Well, right, you know, the union of all those things certainly contains all of R, right? We covered every single point with an interval of length 1, right? The union of those things covers the whole set, right? And so this collection, right? This collection is an open cover of R. Okay, so this is an open cover of R. Okay. Okay. So now comes the hard definition. You have some set K in X. If K has the property that every open cover of K has a finite subcollection that still covers K. So every open cover G alpha has a finite subcollection, let's say G alpha I, from I equals 1 to n, that still covers K. Then we say K is compact. Then we say K is compact. Okay, so this is the really crucial definition. Okay. So every open cover, given any open cover, it's got infinitely many sets in it, say, you can always find a finite subcollection that still covers the set. If your set has that property, we say it's compact. So, to this example, is R compact? Is R compact? No, right? Because here's an open cover. Here's an open cover, and I can't choose a finite subcollection of this that will still cover all of R. Right? There's no way I can choose like 10 billion of these guys and still cover R, right? There's no finite subcollection of this that's going to cover all of R because each of them is only length 1.
Can the elements of our subcollection be infinite sets, or do they have to be finite?
These are infinite sets, right? They've got infinitely many points in them.
Or I guess, can they be unbounded?
Yes, they could be. But the thing is that you have to show it's true for every open cover. So you might say, well, look, I can find an open cover that has a finite subcover, right? Here it is. Right? I'm going to let G sub 1 be the whole set, right? You say, okay, look, I found a cover that has a finite subcover, right? Here it is. But that's not good enough to be compact. It has to be that for every open cover, you always have a finite subcover. Let me just give, I'm sorry to hold you over, but let me just give one example. Okay, so finite implies compact. If you're finite, then you're going to be compact. So suppose you are a set consisting of just one point. Okay. Suppose your set E consists of a single point. Okay. Then give me a cover of it. Give me a cover of it. So somebody says, okay, I give you a cover. It's called G alpha, and alpha. There are uncountably many elements in this cover, right? But I say, okay, just give me one of them, choose one of them that covers X. That's going to be my finite subcover, right? And so I found, right, so I take this infinite cover, and I just choose any one, any G alpha naught that covers X, then this thing is my finite subcover. Right? So if my set is finite, I can always choose a finite subcover. Right? If I had 2 points, x1 and x2, I'd say choose one point, choose one of these sets that covers this guy, choose one of these sets that covers that guy. I've got a finite subcover. Okay? So being finite implies compactness immediately. Yeah.
Was your G sub alpha here in this example about the set of open covers?
G sub alpha was just an arbitrary open cover. So
Okay.
I said, give me any open cover. Like here it is. Like here are my G's. And some of them aren't even covering X itself. Okay. Pretend that these are all open sets. Okay. So there are infinitely many of them. Okay. But I say, okay, you've given me infinitely many of them, but it's a cover of X. So one of them's got to cover X. Right? Choose that one guy. That'll be my finite subcover. Right? My finite subcover will be the set consisting of that one set. Okay. And the cool thing that we'll see soon enough is that in Rn, compactness has a nice characterization that compactness is actually equivalent to being closed and bounded. Okay. So this is the famous Heine-Borel theorem. So compactness in Rn is equivalent to being closed and bounded. But that will take us, I think we'll probably do that next time. Okay, that's it for today. Sorry to hold you over.